What are cell delays? The input-output delays of standard cells depend on a variety of factors, but before we get into that, let's look at the diagram at the bottom of the slide. It defines what is a cell delay of a combinational cell. So if the input, when the input changes, the delay is the delay from the input changing to the output changing. But how exactly do we define it? So there's a very precise definition that is usually used, and the most common definition is it's basically a convention. So there is nothing, there's no science, there's no hard science basis to it. It's just a convention that we pick and we use to define delay. So one very common convention is that you would find the time when the input changes past its halfway point. So the input is going from 0 to VDD. Whenever it crosses 0.5 VDD is your T0. Okay. And then when the output crosses 0.5 VDD is the delay. So the propagate, we call that the propagation delay. So the propagation delay is the time interval between the input crossing 0.5 VDD and the output crossing 0.5 VDD. And incidentally, what is VDD? VDD is the voltage that you're supplying to the gates. Okay, so all the gates switch. When they're switching, when they're going from logic 0 to logic 1 or vice versa, they're basically switching between ground to a voltage VDD. And the halfway point of the transition is what we use to define cell delays. Now this input to output delay, this delayed from the halfway point of the input transition to the halfway point of the output transition, that delay in standard cells depends on the following factors. Depends on what we call PVT, process voltage and temperature. You can imagine that voltage and temperature are easy to understand, so let me start with those. As the voltage that you supply increases, okay, if you're driving, you're basically driving the gates harder by keeping them more voltage. Whenever you provide more voltage, everything gets faster, because when voltage increases, current increases, right? That's fundamental to the way the universe works. When voltage increases, current increases. If current increases, then you can charge and discharge capacitors much faster, and therefore everything speeds up. So higher the voltage, faster everything is. Now, what about temperature? The transistor behavior is very temperature dependent. Whenever you get a deeper knowledge of MOSFETs, you will find that the MOSFETs characteristics, the IV curves of MOSFETs, for example, are very temperature dependent. As temperature changes, the mobility of electrons and holes in the silicon changes, the density of electrons and holes change, and there are lots of things that are temperature dependent in a transistor. So as temperature changes, the transistor characteristics change, and when the transistor characteristics change, the characteristics of the circuits using those transistors changes. So the logic gates, which are based on PMOS and NMOS transistors, their properties, including delays, change as temperature changes. And this dependency on temperature is very, it may not be very straightforward. In some process nodes, lower temperatures make for lower delays. In other process nodes, lower temperatures make for higher delays. So there can be a non-linear dependence of delay on temperature. Okay. On voltage, there is always the dependency is very straightforward. As voltage increases, delays decrease. With temperature, that dependency may not be straightforward, but it's very important to recognize the delays are strongly dependent on temperature. Okay. So that's voltage and temperature. What about process? What is the meaning of process dependency? Now, ASICs are the output of a manufacturing process, right? So this actual silicon that is used in real devices has been manufactured in a factory, in a foundry. And any manufacturing process has some variations. So when you say that a gate oxide thickness is, let us say, 15 angstroms, that is your target thickness. The real thickness that you find may be plus or minus 1, 2, or 3% of that target. Okay, so when you're targeting 15 angstroms, the actual thickness in a particular ASIC may be not 15 but 16 or 18 angstroms. And every parameter of a transistor or any parameter or any physical parameter of a piece of silicon circuitry will have some process variations. Okay, thicknesses, geometrical parameters, but there's always be some plus or minus around a target. Even the dopant density of the N-type and P-type dopants, the dopant density, you may have a target density that you're achieving in the manufacturing process, but there'll always be some little variation around the target. So that combination of all those variations results in the PMOS and NMOS transistors having some variation in their characteristics. And that variation will create a variation in the delays of the logic gates. That's what we mean by process dependency. So the input-output delays of standard cells depends on process voltage and temperature. Okay. Then this delay also depends on the output load capacitance. So any given gate, whatever capacitance it is driving will determine its delay. The higher the capacitance being driven, the higher will be the delay. Then the delays also depend on the transition time at the inputs. Hopefully that is pretty, that should be pretty obvious. And then what may not be obvious is that the delay also depends on what is the type of transition. Is it a rise or a fall transition? So for example, in a, let's say in an inverter, if the input rises, the output falls. You'll have a certain delay for that. But if the input falls and the output rises, that delay need not be the same, could be different. So the type of transition, whether it's a rise transition or a fall transition at the output, you will have different delays for that. And finally, for a given standard cell, delays will differ from input pin to input pin. So if I have a 2-input NAND gate, the delay from input A to output and the delay from input B to output need not be the same. And so these are all the different factors that determine cell delay. Now, flip-flops are what is known as setup and hold time. And maybe I will come back to this topic in a future class because you may not have the background for me to cover this at this point. So let's skip this slide for now. I'll just sort of, for those of you who may have an idea of what is the setup and hold time of flip-flops, I would like you to, I would like to go over what, very quickly what these times depend on. So they also depend on the PVT, just like the delays of combinational cells. But in particular, setup and hold times depend on the transition time at the D input of the flip-flop, and it depends on the transition time of the active clock edge. The setup and hold times of flip-flop do not depend on the output load of the flip-flop. They only depend on the transition times of the D input and the transition time of the clock edge. And again, we'll get deeply into setup and hold times in some future classes.